Okay, so let's take up a concrete example. Here is an example. We just want to write a VHDL description for a AND gate. Okay, so we need to describe the entity and the architecture. What is the interface of an AND gate? Let's give it a name. Let's call it AND gate, and let's say it has two input ports, A, B, and a single output port, C. And we know that it should be a AND of A and B, right? We want to describe this behavior. So once we describe this behavior, we would also like to simulate the circuit, right? So how do we simulate the circuit? There is a thing called test bench. What is a test bench? It's a common engineering term. It's not something specific to VHDL. A test bench just means some way of testing something, okay? Some way of testing. So this is our entity to be tested. We want to test this. So VHDL offers some features for even writing test benches. What we need to do is we need to apply some signal to A. For example, something like this, and some signal to B. And we want to see what the output looks like. We want to simulate this, right? So VHDL actually offers you a way of also describing this. What should be the values assigned to signals? So essentially, what do we do is we describe this entity called the AND gate, which has these inputs A and B and output C, and we instantiate an object of this type inside another entity. We can give it any name, but the common name is test bench. Test bench. This is a very typical name given to an entity which acts as a test bench for this entity under test. This is being tested. And in the test bench, we create a signal. Okay, let's call it X and Y. We connect this signal to A, connect this signal to B. Maybe we can connect another signal Z here. And we can assign some values on X and Y. We can assign a waveform on X and some other waveform on Y. And we can observe the waveform on Z. So this description can also be written in VHDL. Okay. So this is typically the process that is used. You describe the entity, you instantiate it inside a test bench. Test bench is another entity that has no ports. It has no input ports or output ports. It doesn't make sense, right? Because this is the thing that is being tested. Okay. And so whatever is to be assigned is done here, and the outputs are examined. Okay. So the part where you assign a value to the signal. So let me give an example. Let the signal have the name X. So X is assigned 0 and 1 after 3 nanoseconds and 0 after 10 nanoseconds. So this is a statement, it's a valid VHDL statement, but it does not describe hardware. It says the signal X should be assigned these values 0 and then 1 after 3 nanoseconds and 0 again after 10 nanoseconds. So this is a time delay, right? This is a nanoseconds, this is a time delay. So this clearly does not correspond to any hardware, but VHDL allows you to describe such things. So VHDL has two parts. VHDL has two kinds of constructs that you can describe. Those that correspond to hardware, which are also called synthesizable. Synthesis tools can convert this description into a circuit. And there is other code which is unsynthesizable, which is used for describing such things like time delays and so on, which are useful for simulation, but actually which don't correspond to any hardware. So we need to write a test bench, right? So we'll see how to write a test bench because we need to simulate our AND gate. So coming back to our example, we have to write an entity AND gate and we have to write a test bench for it, which is also another entity. So let's go to the tool that we use, EDA Playground. I'll actually code this. So I'm going to search for media playground. This is a walkthrough for how to use the tool. Okay. Okay, so this is the EDA playground window. I have already created a registration. You can create a profile and so on. So let's first select VHDL as our language. VHDL. Okay. My top entity that I'm going to simulate is going to be called test bench. You can give any name, but test bench is commonly the name which is given. Okay. And I will use some tool for simulating it. So let me select the first commercial simulator. There is Aldec Riviera. Okay. I want to run it for, let's say, 100 nanoseconds. And I want to display the waveforms after it runs. So I'm going to enable this option. Okay. Now let's come to this. These are the settings. Now there are two things. One is a file called design.vhd. This is a VHD is a VHDL extension. I'm going to describe my AND gate here, and I'm going to describe the test bench here. Okay, so test bench is going to create a component or object of type AND gate, and I'm going to use it. So let's begin. So begin AND gate is. So remember, VHDL is case insensitive, but nonetheless you follow some conventions. For example, I always begin the name of a class with a capital letter and the component names with all capital letters. Okay, so this is a convention that I use. So entity AND gate is told. Right, so our entity description is over, and then we have architecture. You can give any name to the architecture as well. So because this is a behavioral description, I'm going to call it behave. C is assigned A and B and behave. Okay, so that's it. Now I'm going to write a test bench for this. So in the test bench, I want to create an object of type AND gate. So that can be done using the component block. So we'll see how to do that. Okay, so first let's create an entity. So test bench is also an entity without any ports. So let me just copy this. Okay. Okay, and this is empty. It has no ports. Alright. Similarly, we have architecture. Okay. So now I want to create a component of type AND gate. So let me call it A1. I'm using all caps. A1 is of type AND gate. And then I have to connect some things to it, right? So let me create 3 signals. Okay, the syntax is like this. Signal X, or let me give them names A in, B in, and C out, is of type bit. Okay, and I'm going to initially assign them a value 0. This is the syntax for doing initialization. Okay, AND gate port map. Now I'm going to map the ports of my AND gate to these signals. So I'll enter them in the same order in which they appear in this port declaration: A, B, and then C. So A is mapped to A in, B is mapped to B in, and C is mapped to C out. Semicolon. That's it, right? Okay. Now I want to assign some waveform to A. So if you recall, Okay, I'm just calling it A in, B in and C out. Okay, so and I have to assign some waveform to A in and B in. So here is a way in which I can assign some value. So A in, sorry, so A in was initially 0, so initialized to 0. So I'm going to assign it so after every 10 nanoseconds the value of A in flips. 0 becomes a 1, 1 becomes a 0. Okay. Similarly, B in is assigned. I'm just arbitrarily selecting some time, and C out is what I want to observe, right? That's it. Now one thing is, notice that I am using this AND gate, so I have to kind of tell the test bench entity that this AND gate actually corresponds to this definition, and I have to tell it that it has these ports. So the way to do it is to declare the component. So I have to have a component declaration block. So component AND gate. Okay. I just have this line copied. Alright. So I have declared some signals. I have declared the component, and then I have described the architecture. So in the architecture, I have created an instance of this component AND gate, and I have connected the signals to it by using the port map. I have mapped these signals to its ports and assigned some values to the two signals. Okay. So let's try to compile it. Surely there will be some compilation errors, right? There will be some syntax errors in this. So let's see. Okay, so let's run this. Oh great, so there were no errors, right? There were no errors here. Okay. I have to rerun this. Disable my pop-up blocker and rerun this. So when I run this, because I have selected open EP wave after launch, this will automatically open the wave window. And notice that I had requested A in to be toggled after every 10 nanoseconds. So that's what's happening. It's 0 and then 1 and then 0, and this time period is 10 nanoseconds. Similarly, B in was to be toggled every 13 nanoseconds. Now let's look at C out. This is 1 only when both A in and B in are 1, and otherwise even if one of them is 0, it falls to 0. So C out is clearly following this. C out is mapped to the port C, which is exactly same as C out. So C out and the C are same, right? So this is clearly working. So one way is to visually examine and check if it actually works as a AND gate. So it is. C is 0 when either of A or B are 0, and it's 1 only when both are 1. So it's working as a gate. So now you can save your code, okay, and there's way to save it if you sign in here. So this is an example of using EDA Playground for writing an entity and a test bench. Now notice one thing, there are some lines already present when you start typing. This is a library declaration. Okay, it's like saying import library name in Python or include stdio in C, for example. So you declare some library code that you use. So in this current example, this is not being used. Even if you remove it, it will be fine. But in a lot of future examples, this is necessary. So we'll keep it here as it is. Okay. So that's it. So we have seen how to model this simple AND gate, write the entity and the architecture in EDA Playground and simulate it, and how to observe the output waveforms. So let's take a more complicated example. Let's take the example of a half adder. Okay, it has two outputs, and we know the behavior of the outputs. We know that it should be an XOR and AND. So how do you write a behavioral description and a test bench for this. So here is a code to model the same. In the design file we can describe the half adder circuit, okay, and in the test bench, again entity test bench, we copy this as a component declaration, okay. We declare some signals, then we instantiate the half adder, give it some name, map the ports. Notice this is another syntax to map the ports. This is explicitly saying port A should be mapped to signal A in, port B should be mapped to signal B in, and so on. This is a right pointing arrow. This is a left pointing arrow which is used for signal assignment, and the right pointing arrow is used for port map. Or you just enter the signal names in the same order as the port names. So both are two ways in which you can do a port mapping. So this is also same. This time is arbitrary, it can be anything, okay. And maybe we can see what this looks like. I have this saved. Okay, I have saved this in one of my designs. So this half adder circuit has been saved. Let me simulate this and see what the output looks like. So this is the output. We have A in, B in, and this is C out. Carry out is an AND of the two, so it's one only when both are 1. And we have sum out, which is an XOR of the two. Just ignore these three, they were added as an example. Maybe I can remove these signals, okay. So we have A in, B in, C out, and S out, which can be plotted here. Okay. So let's move on to the exercise for this lab. The exercise is the same, to build a half adder, but to use AND gates, OR gates, or XOR gate as component. So design an entity AND gate, design an entity XOR gate, declare an entity called half adder in which instantiate the components for the XOR gate and the AND gate, connect them together, and then instantiate the entity half adder into an entity called test bench, connect them to these signals and simulate it, okay. So the task is to write a structural description of a half adder. In the previous example, we described the half adder as a behavior. We just said the sum should be A XOR B and carry should be A and B. We did not describe these as interconnection of components AND gate and XOR gate, right? So you are supposed to write an entity AND gate, describe the architecture, an entity XOR gate, describe the architecture, create two instances, connect them together, connect those to the output sum and carry, and then create a copy of this half adder in the test bench in a similar way. So that's the exercise. So this is the exercise for the first lab.